In yesterday's class, we saw this really very direct way of computing a line integral, f dot dr, by taking by parameterizing our oriented curve, stuffing that parameterization into the vector field, taking the dot product of that with the velocity vector to our parameterization, and then integrating that result with respect to t. That is a way of computing a line integral that will always work as long as we can come up with a parameterization for our curve. But very often it's messy and nasty, and it's not always the best choice. Today is going to hopefully feel a lot lighter than yesterday, because we're going to come up with some methods of computing line integrals that don't rely on that direct form of computation. And so that's going to take two different flavors. The first, and these flavors are related, by the way, the first is that we will look at path-independent line integrals. So for certain vector fields, it will be possible for the line integral to depend not on how we get from the starting point of our curve to the ending point of our curve, but just depend on the starting point of the curve and the ending point of the curve. Those are our favorite vector fields in the universe. They're called path-independent vector fields. And so for those, we don't have to have a parameterization for how we get from point A to point B, because it doesn't matter how we get from point A to point B. It only matters what is point A and what is point B. And so what we're going to discover there is the first of our fundamental theorems that populate this last chapter of vector calculus, called the fundamental theorem for line integrals. And it has very much the same flavor of the fundamental theorem of calculus, the ordinary version, where if we have a path-independent vector field and we want to find the line integral from point A to point B, we just have to find an antiderivative of that vector field, evaluate it at point B, evaluate it at point A, and subtract those results. So it's just like the ordinary fundamental theorem of calculus. And the only question is, what does an antiderivative actually mean in our case? Well, it's that same kind of antiderivative that we saw a couple of sections ago when we were studying gradient vector fields. Because as it turns out, gradient vector fields are the ones for which we can do this technique. If we want to find a path integral of a gradient vector field, we can just find its ungradient, right? Find its antiderivative that in the sense that it's an antiderivative in the sense that our field is the gradient of some scalar potential function. And that scalar potential function then plays the role of the antiderivative in the fundamental theorem of line integrals. So for a gradient vector field, the line integral along a path from point A to point B is nothing more than the difference in the scalar potential function between the point B minus the point A. So that's the fundamental theorem of line integrals, and that's going to be our first step for today. The second step and the third step both give us some options for what to do when our vector field is not path independent, when it's not a gradient vector field. Are there other ways that we can do this? And the answer is tentatively yes, except that here we're going to require that our path from point A to point B is not actually a path between two different points, but actually needs to be one of those closed curves so that we can measure a total circulation around a curve. And so Green's theorem is going to be a way of taking a circulation integral, so a line integral of a vector field around a closed path, even if that vector field is not a gradient vector field, and computing the circulation by, instead of doing a line integral around that simple closed path, what we replace it with is a double integral. So your decision whether or not that's an easier or a more challenging thing to do, but we can replace it with a double integral on the region of the xy plane inside of the path that we chose. Right? So that's the sort of good news, is instead of setting up an awful looking path integral and computing it directly, we can replace that path integral with a double integral on the region inside of our path. And the integrand, what we are integrating in that case, is the circulation density, is what our textbook authors call it. I call it the scalar curl of our vector field. So what we end up doing is we compute this scalar curl, which is like a derivative of a vector field, and we end up integrating that derivative on the region inside of our curve. And the answer that we get is exactly the same as the answer we would have gotten by finding the circulation around that simple closed path. And so that's Green's theorem. So we have today two really powerful tools to avoid having to directly compute line integrals. The first one, on using the fundamental theorem, we can use if we're using a gradient vector field. So if our vector field is a gradient field, we can use the first option. The second option, to use Green's theorem, is an option whenever our path is a simple closed curve, right? When we're not going from point A to point B, but we're going from point A back to point A. we can measure the circulation using Green's theorem to replace our path integral with a double integral that is often easier and more tractable to do than the original path integral along a parametrized curve.